Excellent. Welcome, everyone. Thank you for joining us. This is a webinar called Solar PV Hosting Capacity Using Traditional Solutions. This is part of the ARENA project, Advanced Planning of PV-Rich Distribution Networks. We would like to first thank ARENA. This project received funding from the Australian Renewable Energy Agency under its Advancing Renewables program. And also, it's important to say that the views expressed here are not necessarily the views of the Australian government, and the Australian government does not accept responsibility for any information or advice contained herein. And of course, we would like to thank AusNet Services. They are funders as well of this project and collaborators, exchange of data and know-how. And of course, we would like to thank the University of Melbourne, which is the organization that we work in. Okay. This particular webinar will be presented by Dr. Andres Procopio and myself, Professor Nando Choa, both with the University of Melbourne. This webinar in particular is presenting and focusing a task called Task 3, Traditional Solutions of this project, Advanced Planning of PV-Rich Distribution Networks. We gave a workshop recently in end of March that was for specific stakeholders, and we decided also to provide this webinar to the public so the corresponding content can be disseminated. There's a report available online, but with the webinar, you can have a glimpse, a summary of what the report is providing. This particular task was developed by 3 members of the team, our research team, Dr. Andres Procopio, as I mentioned, myself, and also Dr. Kyriakos Petro. All our projects, more information, reports, and also the publications, the report itself or papers, they can be, most of them downloaded from that website there. Okay, the outline of this webinar that should last approximately 1 hour is the following. So first, we're gonna just set the scene, with a very quick context about solar photovoltaics and hosting capacity. I will present the overview of the project, and particularly very quickly, the main aspects of task 1 and task 2 that are before, of course, task 3. Then we will move on to task 3, where I just will provide a very quick overview, but most of the corresponding work and the methodology, and as well as the corresponding results, will be presented, of course, by Dr. Procopio. Then we will finalize with the conclusions and the next steps. All right, so solar photovoltaics and hosting capacity. First, we need to have some definitions. What is hosting capacity to start with? The maximum amount of solar photovoltaics that a given distribution network, or part of it, it could be a feeder, it could be a low voltage feeder, that can host without negatively affecting its normal operation at any point in time. So that's how we define hosting capacity in terms of solar photovoltaics. Now, without negatively affecting its normal operation can have as well different aspects to be considered. So for instance, voltage statutory limits, if we're looking at solar photovoltaics, we don't want to go for residential customers that have a maximum of 253 volts or 10% above nominal. You don't want them to go beyond that. So that would be let's say a normal operation up to that point. However, you also can look at asset utilization. You want to avoid congestion. You want to avoid assets to be overloaded. But there are many other things that can be considered, protection or harmonics. But in the context of this particular study, we'll be limited to the voltage statutory limits and asset utilization. Now, in terms of the amount of solar photovoltaics, there are different ways of as well considering this. It could be the kilowatts of a given network or the megawatts that are all installed in that particular area. But what we are going to use throughout this particular webinar and on all of our reports corresponds to the percentage of customers with photovoltaic systems. That means that if we are looking at a particular feeder with, I don't know, 100 houses, 100 customers, then if 20 of them have photovoltaics at a given, for a given scenario, then that's 20% of penetration. So those are the definitions that we will be using and the considerations that we'll be using for the whole project. Now, in terms of impacts, I guess that just to provide the basics here, this is a little diagram of a low voltage feeder. The thing is that our low voltage feeders, they have been designed and well, in general, distribution networks around the world have been designed to cope with the maximum load. And that means that when people come back home, for instance, at 6 p.m., or if it is a very hot day, the demand of all these houses is such that, of course, will drive the voltages down, or will drive more currents, but the system has been designed for that. The problem is that if we have a weekday where no one is at home and we have some solar photovoltaic installations, then you can have the radiance simultaneously hitting all these rooftops. And then, of course, the generation will be also simultaneous. And depending on that penetration, you might have reverse power flows that bring the voltages up. That's the voltage rise issues that everyone talks about. And the corresponding flows also can be much, much higher than what the actual conductors and the transformers have been designed for. And that is, of course, a challenge for network operators. Now, the problem is not just limited to low voltage feeders or our low voltage networks. It is throughout the distribution network. So the moment that we have multiple residential areas with significant penetrations of photovoltaics, of course, the same effects are going to be seen at the high voltage. So we're talking about 22 kV or 11 kV, for instance. Of course, there will be other type of consumers that might be absorbing those reverse power flows, but the principle is that the challenge will be seen throughout the networks. And well, the big question will be, of course, how can we determine the hosting capacity of the networks? And how can we increase the hosting capacity of our networks? So those are the key questions that actually we are trying to answer with this project. So the project started in February 2019, a little bit more than a year, and still has a little bit less than a year to go. There were two main aspects. One was the production of analytical techniques to assess network hosting capacity. That is really looking at clever ways of using smart meter data, historical smart meter data, and actually that corresponds to task 2, and we will discuss that very, very briefly. But then the other part, which is, I would say, the largest part of this project, is the planning recommendations. But for us to really provide planning recommendations to DNSPs, distribution companies in Australia and around the world, then you need to assess what it is considered traditional and what is considered non-traditional, so then the new things that could be done. And for you to really provide these recommendations, what we want to do, of course, is create first quantifications of the benefits of each of these potential solutions and then compare them. And that's what really our tasks are about. First, we start with the modeling of the networks. So this is very interesting modeling that we'll discuss in the next few slides. Then we move on to the analytical techniques using smart meter data. Then we are assessing the traditional solutions, which is this webinar about. Then we will move on to the non-traditional solutions. Finally, we'll be doing comparisons in terms of cost, and we will consolidate the findings, which is really the planning recommendations for distribution companies. So far, we are around 60% done in the project. So let me take you through task 1 very, very quickly. The report is available. There's a link there as well. And what we were doing here really was the modeling, the very detailed modeling of high voltage feeders. So these are 22 kV feeders. Now, of course, each DNSP around the world, they will have hundreds, if not thousands, of high voltage feeders. For the particular case of AusNet, that is our project partner, we went through an assessment of the different characteristics of their high voltage feeders, and with their knowledge as well of data availability and the different characteristics of these feeders, we decided to go for feeders that were, let's say, in the extreme of the spectrum of characteristics. So those that were very different, very rural and with very, very long feeders, for instance, or urban, extremely dense. So the idea here is that by selecting feeders that are significantly different from the whole population, whatever happens to them will represent the extremes. And then therefore, anything else that is, let's say, with milder characteristics should be even better. So that was the premise here. And we did that with the collaboration of AusNet. We had to, of course, once we decided what are the most adequate high voltage feeders, we translated from SynCal to using a translator through Python and ended up with OpenDSS, which is an open source software that developed by EPRI in America that allows us to really have very, very detailed analysis of distribution networks, three-phase, unbalanced, multi-voltage levels, etc., etc. So we ended up with multiple networks. So these are graphs that are showing both rural, urban, short, long, etc., etc. These are large networks, each of them with more than 3,000 customers. And of course, to really get into the details of what would happen to particular residential customers, so at the connection point, there are single-phase connections in most cases, we created what we call pseudo-low voltage networks. So the data itself of the low voltage networks in terms of the corresponding conductors and topology that wasn't available by AusNet. Unfortunately, most distribution companies in the world don't have this data necessarily. It might be in GIS, but not necessarily for electrical analysis. So what we decided is to just use our know-how, design principles used here in Australia, and we created pseudo voltage networks. They are not the same, that's a caveat, but they are pretty good. And of course, all this modeling is three-phase and balanced, and that allows us to be very realistic. Now, in task 2, as I mentioned, it was all about trying to come up with very interesting ways of exploiting smart meter data in the context of hosting capacity. Now, the first challenge here is that as much as there is smart meter data in Victoria, because of smart meters, of course, there are a lot of challenges when it comes to privacy, of course, but also in terms of the data that is available. Sometimes there are data that is not necessarily that good, etc., etc. So it was very challenging. And remember as well that as much as there can be smart meter data, P, Q, and V, it doesn't necessarily mean that you have the exact network model of that. As I was mentioning, our high voltage feeders had these pseudo low voltage networks. So there was a mismatch. So what we needed to do was to create what we call hybrid smart meter data. So we had very realistic, actually, smart meter from different type of residential customers, but we had only their P and Q data, active and reactive power. But the moment that we are able to put this into our network models, we run power flows and we could produce a corresponding voltage. So we ended up with P, Q, and V. Lots of data for different penetrations, like 1 billion data points, or more than 3 gigabytes. And with all this data, then we were in a position to really start understanding what, for different penetrations of photovoltaics, what data could be used to really sort of predict or estimate what is the hosting capacity of each network. And that's precisely what we did in this task. So this slide here is just showing that, I mean, we end up with so much data, but we figure out that actually that the data that was mostly correlated was the maximum daily voltage of a given low voltage network. So that daily maximum voltage is just 1 single point per day of multiple customers in downstream a single low voltage transformer, and the corresponding aggregated power seen by the corresponding distribution transformer. So it could be, of course, withdrawing power if it is just load led, or actually injecting power to the network if there's a lot of photovoltaic penetration. So there was a strong correlation there, and we used this correlation to create a very interesting figure that essentially is representing on the y-axis the voltage level, the maximum voltage level seen by the customers of a given low voltage transformer and the corresponding feeders, and in the x-axis what we call the diversified imports of exports. This is just the average of the aggregated power seen at the corresponding transformer. So it's the average of what each customer would be doing. So these little circles there in blue, what they represent is actually smart meter data that you have at that point. So if you have all these points, then you could actually produce with regression techniques an approximation of what might happen. So you are really doing a regression of what might happen for other diversified imports or exports. And by doing that, then you could, of course, like let's suppose you choose 0.3, it goes up, gets to this line here, and with 0.3, you will end up with perhaps around 1.0325 per unit. So that's the idea. And that's interesting because it means that then we could actually assess, because we have this hybrid data for different penetrations, what would happen or how accurate could it be, this hosting capacity. I mean, in the y-axis here in this particular figure, it's going up to 1.04, but imagine if we have it, up to really high voltage levels that to then understand where we're hitting the hosting capacity. And this is what exactly we're going to do. So here are some results. This corresponds to CRE21, which is an urban network, and this is just for one low voltage network with, of course, dozens of customers. Now, the important thing here is that, although I'm saying here that it's one low voltage network, actually the whole assessment is done for the whole high voltage network. But the data that we pick is just for that particular low voltage network. Now, if you pick that data for that particular low voltage network, and you pick the data that corresponds to only around no more than 20% penetration, so in time perhaps it's equivalent of 1 year in our simulations, but could take more years depending on how penetration grows. So in this particular graph, the top left here, what you have is that for that amount of data, the hosting capacity, this is this big red dot, is approximately 2.81 kilowatts. So that means exports of 2.81 kilowatts per customer will end up with around 1.1 of maximum voltage. So that's your hosting capacity. Now, this is an estimation with that amount of data, but in reality, the more data that you have as penetration increases, the more accurate you might get. Of course, because this is simulation, we can actually find the actual hosting capacity, which is in this bottom right figure, that is approximately 2.47 kilowatts per customer of export. That's the actual hosting capacity when you really hit with our models that are corresponding maximum voltage of 253 volts. Now, this is the actual, but this actual is actually not that far from our estimations that we have with 20% or even 30%. Yes, they are not the same, that's true. But that means that if we assume that we can trust to some extent these approximations of what the hosting capacity would be, we can be in a very good position to prepare for these problems that are going to come. So that's the idea of this particular analytic technique, and that this whole methodology that is very well specified in this report of tasks 2. With just around 20% of penetration and the corresponding smart meter data, we can more or less predict the corresponding hosting capacity, because this 2.8 kilowatts, if you multiply by the corresponding number of customers, that will give you an amount of export that then can be actually related to the existing installations, so as to know what are the installations that you could install further than that. So that's the idea behind this. And well, we also have another webinar. There's the link here as well. Should be as well available and Googleable as well on our websites. But in general, I mean, the thing is that with these analytical techniques, we can actually deliver this particular hosting capacity using smart meter data only. So we were using the simulations to understand the data and to trying to find the value from the data, but the technique itself doesn't require any simulations. So you can do this with your existing smart meter data. Of course, it's not perfect. And of course, it doesn't necessarily work with all the type of potential cases. There's more details on the report, but it's actually a very, very good starting point if we want to use just smart meter data for hosting capacity. Well, that was task 1 and task 2. The most important part of this webinar that is now going to start is task 3. The report is as well publicly available, and all the details, the technical ones, are going to be presented by Andreas. So I'm just going to provide a quick overview here. So this particular task that is called traditional solutions was set to investigate the effects and benefits of 3 particular solutions that we call traditional, as in what normally distribution companies around the world do. However, before I get into those particular solutions, the context here was that we were using, and we are using, for all our simulations, the new Victorian PV inverter settings that started to be required from December last year. Now, this is very important because these are quite interesting settings that actually, well, all inverters are capable of doing or following, but these settings actually are bringing interesting benefits that we're going to discuss in the next slides. Now, with those settings, on top of that, because they are not necessarily perfect, we can do even more things. And what we were exploring is the use of offload type changers, which is something that distribution companies do around the world. They changed the offload tab position. The adjustment of the onload tab changers in the zone substations, also known as primary substations. So that is another option that is actually being considered and by distribution companies around the world. And of course, the obvious network augmentation, the more bigger conductors, larger transformers, this is also an option. Now, we did all these studies for the 4 different high voltage feeders, all with the low voltage part as well, that I mentioned from task 1. And we did as well 2 types of analysis that Andreas will present in more detail. One is the single day analysis to demonstrate the time series behavior, but also the seasonal. It's extremely important to really understand what happens across the year, because one thing is to solve a problem that might happen in the worst case day of the year. Another thing is to understand how this solution affects customers, particularly in terms of curtailment throughout the year. This meant that we ended up doing more than 260,000 power flow simulations, more than 360 hours of simulations. Lots of work. Now, the key findings, I'm kind of stealing the thunder here from Andreas, but this is quite important that we might repeat again and again throughout the webinar. The new Victorian settings are fantastic. They bring great benefits, not just to the networks in technical terms, voltage rise, but also to customers. Why is this? First of all, in terms of hosting capacity, at the very least, in all the networks, you can achieve 20% of penetration. Now, that might not necessarily sound a lot, considering that in different parts of Australia, we have even more than that. But what we're saying is that 20% will ensure that there's not even a tiny bit of voltages above the limit, above the 253 volts. And this is fantastic. This is quite an achievement. In reality, actually, we know that there are houses that are seeing more than this, sometimes even without photovoltaics. So that means that actually we could even go beyond this 20% if we're a little bit more relaxed about this limit to some extent. So these are really good news. Now, this comes with minimal curtailment, less than 2% annual. And this is fantastic because it means that the return on investment of people that are buying these technologies to install them on the rooftops of their houses is not affected at all. I mean, less than 2%. There are some outliers, of course, but in general, that's the average that we have seen. And this is really great news. There are some issues, of course, reactive power. I just will mention this. Now, the moment that we put the additional solutions, they bring additional benefits. And that's interesting because then we can move to at least 40% of hosting capacity. And this is quite significant. So by going with solutions that distribution companies around the world are already very aware of and already using, we can ensure that we can have at least 4 out of 10 houses with solar photovoltaics. Of course, this is in the context of having the new Victorian settings, all right? That's very important. With these added solutions, we also see less curtailment, which is also fantastic. And of course, similar to the previous bullet points, we can even go beyond 40%, as a matter of fact, if we are not that picky about the extra volts beyond the 253. So this is quite interesting and very, very promising results. Now, finally, in terms of augmentation, which is another traditional solution, there are benefits with respect to asset congestion. That means that in terms of voltages, we have seen very, very little. So overall, a combination of augmentation and offload tab changers, we believe is perhaps the best combination of solutions, of course, in the context of using the new Victorian inverter settings, and this can take us easily beyond 40%. This is where I stop. I'm going to give control to Andreas so he can give you all the details about task 3. Thank you.
Thank you, Nando. So thanks for the quick introduction, Nando, here on this. Let's move into more of the technical details of this task that we had. And given the fact that we have a lot of information coming through the next slides, this slide here tries to give you an overview of what is coming, what is following. So we're going to start with the methodology of the traditional solutions that we have investigated, which is how we are adjusting the offload tab changes on the low voltage substations, and how we also adjust the onload tab changer on the primary substations, the zone substations on the high voltage side of the networks. And then the third one is, of course, the network augmentation. What is the process that we are following once we identify any technical issues such as voltage rise or thermal congestion of any assets? How do we replace them? And once we have that, we're going to move into the data and the considerations that we have considered for this particular task, which is referring to what kind of demand information we use to model our networks and our customers, generation, forecasting in terms of penetration, how many customers will have PV systems, and how would we increase that throughout the years. And of course, at the end, we're going to focus on to the case studies and the results from all these different methodologies that we have applied. We're going to try to see the effects and the benefits first once we adopt the new Victorian PV inverter settings. And to really do that, we have to first show what is the effect once we have the current settings before December 19, which they don't really have the volt var enabled. And after that, we're going to see the effect once we have enabled the volt var with the new settings as well. Second one will be understand the effects and the benefits of once we adjust the offload tap changes on the lower substations. And finally, the network augmentation results to understand what this means to the customers and the network as well. So as I said, we're going to start with the first methodology, which is how we adjust the offload tap changes. So given that first of all, let's consider what is an offload tap changer. Essentially, it's a device on the transformer which supplies customers in a particular substation, which has the ability to reduce the voltage source mechanically. So essentially, we have the ability to manage the voltage at the source. And this has to be done manually. So some engineer have to go over there and change the taps accordingly. And to do that, first we have to understand how much more we can reduce the voltage from the source. And this allows us to create more headroom for the voltage rise once new PV systems come into the networks. And to do that, we are using a peak demand day. We can imagine we have, let's say, smart meter data from a peak demand day. We're using this information where we can identify the minimum voltage among all the customers that are supplied by a corresponding substation transformer. And then from that minimum voltage, we will be able to understand what is the maximum legroom that we can reduce the tap settings. And to do that, we have the legroom, and we divide it by the amount of voltage change that each of the taps of the transformer will have. And that will give us an understanding how many taps we can go down and therefore increase the headroom of voltage rise. And for this to give you more understanding, we can consider these figures here, where essentially it shows a case where we have unchanged tap positions. It's working as normal. And we can see that we have a headroom of around 2% of voltage rise in this particular case. And we have a lot of headroom of legroom where we can reduce the voltages lower and therefore increase that headroom. And this is actually what is happening. We identified that we can actually reduce, in this particular case, 2 taps, the transformer, and therefore this will allow us to increase the voltage headroom to 7%. So essentially, we increase, we allow the higher voltage rise to come into the network without impacting the voltage limits. So that's the first methodology. The second one is by leveraging as well the on-load tap changer on the primary side of on the high voltage side of the networks, which is called the zone substation. So given that this action of changing the on-load tap changer will affect all the downstream transformers that they are equipped with off-load tap changers, and someone has to go manually change all this, we have to first understand. We have to first start by changing the on-load tap changer, and in this particular case, we're reducing by the voltage target by 2%, and then we're running a simulation to see what will be the effect in terms of voltage level on downstream. Once we know what's the level there of voltage, we then adopt the first methodology that we explained previously, where we reduce even further the offload tap changes to create more headroom for the voltage rise. In this particular case, we have exactly the same scenario where we had just 2% of headroom in terms of voltage rise. And by leveraging both on-load tap changer and off-load tap changers, we can increase that headroom to 8%. Compared to the previous case where I only had the off-load tap changers, we are gaining extra 1% of voltage rise headroom. So this gives an understanding that we can create more room to accommodate more PV systems that they're creating voltage rise phenomenon. So the third one is the network augmentation. And for the network augmentation, what we do is essentially we're running time series analysis. And in each time step, we stop and check if there's any asset congestion. If there's any asset congestion, or like transformer or conductors, we move into replacing that conductor with a higher impedance, a lower impedance, and ampacity. And for the transformers, we replace the transformer with a higher rating transformer. Now that we have replaced these assets, it means that it might, for example, reduce also the voltage level or the voltage issues. So we run another simulation to see if that will create benefits to the voltage level. And if it's not, we check for voltage issues. And if we identify any voltage issues, we start replacing from the head of the low voltage substation. We start replacing in terms of 100 meters every time the conductors, and we replace them with lower impedance conductors. So essentially, we are lowering the voltage rise effect on those substations. And we repeat this simulation until we have solved all these problems. Some of those might not be solved, and given that we don't have infinite amount of options in terms of conductors or transformers, so that will stop if there is no other option. However, it will continue until it solves the technical issue that is faced at that particular moment. Now, in terms of the data, in particular the demand information, in these particular cases, in the high voltage feeders that we have for our simulations, we have two types of customers. We have residential customers, which is the majority of our demand, and also we have non-residential customers, which are ranging from hospitals, malls, small offices, etc. So to really model the residential demand, we are using real smart meter data, anonymized, that were provided by AusNet Services. And for that, we are referring to P and Q values that we have extracted from smart meter data. And we are using this information to really model the demand behavior of residential customers. For the non-residential, we're using open source information that is provided by CSIRO, that they have collected information of demand behavior from different non-residential customers. Now, for the solar PV, we are using two types of irradiance profiles. The first one is the clear sky irradiance profiles, where essentially we can create these clear sky irradiance with a very high accuracy using a tool that was provided by the University of Loughborough in the United Kingdom, which allows us to set up specific settings for our PV systems and also the location and these PV systems are located. And by that, we can create high resolution clear sky radiation profiles. Why do we use that? This is because we want to use them into the single day analysis, where we want to see the time series behavior of the different methodologies that are going to apply. And also we want to understand the worst case scenario. And what I mean by worst case scenario is the moment where we have peak generation and low demand. This will allow us to understand the range and the extent of the technical issues that are facing the networks, and also understand to what extent the methodologies of solutions that we're going to apply might provide benefits. So the second part of information we're using for solar PV systems is essentially actual radiation profiles that they were provided by AusNet Services. And clearly in these particular figures here, you can see that we can see the peak generation, peak irradiance profile, which is provided per unit, is slightly lower than the one that is shown here on the left, which is the clear sky radius. And this is because in these particular profiles, which are actual profiles, the weather conditions are already embedded. So this means that we have cloud effects, that they are actually reducing the magnitude of the irradiance, and also the clouds are creating that intermittent behavior between each spike throughout the day. So these profiles are used for our seasonal analysis and allows us to create a realistic environment of simulations where we can see the benefits and the effects of the different methodologies throughout the whole year. And by doing that, we can easily understand what is the effect on the customers, especially on curtailment, which is something that the customers need to be aware with any methodology that we can apply in terms of solutions that they will benefit the network. So once we have this information of how we can model the behavior of the PV systems, now we have to see how we are essentially modeling the increasing penetration of PV systems in this network. And for this particular task, what we're actually using, we're using actual forecasting information provided by AusNet Services. And what this information is saying, and I will particularly focus in one of these cases here, one of the networks that are using an urban network. What the forecasting is saying is that AusNet Services were able to provide us with the actual information of how many customers have PV systems in this particular network by 2018. And from that moment on, we have forecasting information up to 2030. And this refers to the percentage of customers that they might adopt this technology, PV systems, by the corresponding year. And given that we didn't have any extra information because we want to simulate up to 100% of customers having that technology, we expanded that forecasting up to the point where all of the customers, 100% of the customers, adopt PV systems. And this, from these forecastings, where you can see the penetration level and the corresponding year that is expected to be seen, that penetration, we are using them to model our analysis. Essentially, we are modeling all this penetration throughout the years, and you will see later on in the corresponding results where these penetrations are related as well with the year that is expected to be seen. Now, in terms of the corresponding panel sizes and inverter settings that we are using for these PV systems, we are using only single phase PV system installations, and these correspond to residential customers. And the panel sizes range from 2.5 to 8 kilowatt peak panel sizes, and these are corresponding to the current statistics in Australia of PV system installations. And the corresponding proportion of all these statistics is shown here, which range from 8 to 16% accordingly. And given that in several states here in Victoria and several DNSPs are already understanding that the extreme reverse power flows from PV systems might lead to technician to the networks, they have come into different export limits that they're imposed to these residential customers with PV systems. And in particularly here in Victoria, and in the case of AusNet Services, we have a limit where residential households with PV systems have a 5 kilowatt peak export limit, which means that customers with PV systems cannot export more than 5 kilowatt of power into the grid. And to really model that, we are assuming that we have inverter sizes that they are capped to 5 kVA. And to give you an example, if one customer is allocated an 8 kilowatt peak PV system, the size will be 5 kVA. This means that at the corresponding peak generation, that the customer could supposedly produce 8 kilowatts of power, he will be limited to 5 kVA to model the export limits. On top of that, we are also considering the new Victorian settings of VoltVAR and VoltVAR, which are considered to be the default settings once someone installs a PV system in their households. And also in the simulations is considered to be the default setting once we allocate a PV system in a customer. And to give you an example of how these new settings operate, essentially the first function that is actually kicking in is the VoltVAR, which essentially starts to absorb reactive power as soon as the voltage at the connection point of the customer increases from 241 volts, which is 1.04 per unit. It starts absorbing reactive power up to the point of 1.1 per unit of voltage, which is the limit of the voltage, the maximum limit of the voltages. And by that moment, given that the absorption of reactive power might not be enough to really reduce the voltage below the limits, up to 1.1 per unit, the VoltVAR kicks in, where it starts from that moment on, 1.1 per unit, to curtail generation linearly down to 259 volts, which is 1.12 per unit, which by that time, the PV inverter is limited to 20% production of active power, corresponding to the rating of the PV system. So these particular settings are the new ones that are actually adopted now in Victoria since December 2019, and are used as a default in our analysis. In terms of documentation data, what we are using commonly used assets by different DNSPs in Victoria, where we have a number of conductors for the high voltage lines that we have for 22 kV, and also for low voltage conductors, which are up to the 400 volts. And for distribution substations, depending on the connection type, single phase or three-phase connection, the size of it, we have a range of different transformers that we are considering in this augmentation analysis. Of course, you are seeing here just the a brief description, an overview of what the assets are we're using here. Behind this, we have a detailed modeling of all the impedance levels, the R and X ratios, and everything of all these assets that we are using. So now let's jump into the more interesting stuff, where we'll be able to see the effect of all these solutions that we are talking about. And first, we're going to start with the effects of and the benefits of adopting the new Victorian PV inverter settings. As Nando mentioned earlier, those settings were found to have significant benefits to both networks and customers, and allows us to accommodate up to 20% of customers with PV systems. And this is done with a minimal curtailment, and we're talking about the range of around 2% of annual curtailment with these particular settings. And with this, it allows us to reduce the magnitude of voltage that we are seeing in the networks, and also the number of customers that are not compliant with the standard, that they are actually facing voltage issues, is becoming lower. However, given that we are absorbing active power with the new settings, and we're going to show later on what this means, it's increasing the current flowing into the network, and in combination with the active power, the generation that we have, which is also increasing the current flow into the network, it might create some risks of overloading some of our assets. So let's start first. Before we actually go and show the benefits, we have to really understand what are the effects and the behavior once with the previous settings, where we only had the volt-var function enabled without any volt-var function working at the same time. So this will allow us to compare the simulation results. So here we have a single day analysis, which essentially it takes the worst case scenario for a particular season and also different penetrations. So we have the seasons here, and the penetration increases throughout the time. So we are using steps of 20% penetration increments, and it goes from 0 to 100%. And on top of that, you can also relate the forecasting of what year this penetration might happen. And what you can see here is that the voltages, as we increase the penetration level, they are increasing as well. And we can see more and more of these voltage profiles violating the statutory voltage limits, the upper statutory voltage limit. And the majority of these voltages is always higher than 256 volts. And we have a large number of customers being at that level. So in terms of the high voltage utilization levels, here we have the conductors, the utilization level of each one of the conductors in the high voltage side of this network. And what you can see is that we don't see any of these assets to be congested. And this is because we are only having the volt-var function that is essentially trying to curtail as much as possible of generation to keep the voltages within the predefined limits that we showed previously in this corresponding settings, is significantly reducing the utilization level of the assets. Of course, you can see at 0% penetration, we have this specific utilization level that goes up to 35% of utilization level. And once we have PV systems in the network, naturally, because we are generating power at the customer's locations, that reverse power flow or of generation is consumed locally, and therefore is reducing the utilization level of the assets. However, as soon as we increase the penetration, where the generation is becoming higher than the demand, the local demand, this will lead to higher utilization levels. But again, as we said, given that we're curtailing significant amount of generation, the utilization level of the assets is always contained within the limits. Now, here we have a slide which shows for each individual customer in this network, which we are talking about more than 4,000 customers, that they have PV systems. We are seeing the active power generation from their PV systems. And what you can see here, if a customer was not having any of these solutions, any volt-watt function or whatsoever that it will allow, that it will reduce the corresponding generation, these figures here will potentially show a bell shape where actually the customer is generating the maximum that they could given their PV system installation. However, in this case, we are seeing a significant reduction of generation for each of the customers here. And as soon as we increase even more the penetration, we can see significant impact to these customers because they are curtailed even more, because the voltages from a large number of customers located in this network are pushing the voltages up, and therefore everyone has to contribute into curtailment to reduce the corresponding voltages. So this is the effect of adopting only the volt-watt function, which was actually the practice before December 2019. Now, we are moving into understanding what might mean if we enable the volt-var function in combination with the volt-watt function, adopting as well the new settings that were defined by the DNSPs here in Victoria. And those were effective from December 2019. Now we have exactly the same scenario here, where we showed previously, where we have the customers being we'll have the customers using also the new settings that we referred previously. And what we can notice here is that the voltages in general, the magnitude of the voltages is reducing significantly compared to the previous case. And not only that, the number of customers that they are actually facing voltages above the limits is significantly lower. And on top of that, we also see that the voltage, the magnitude of the voltage level is never going above 1.11 per unit, even at the worst case scenario. And just to compare this effect of enabling the volt-var with this particular case, we are showing here the effect without having the volt-var. That was the case in the previous slides that we showed. And essentially what you can notice is that the magnitude and the number of customers that are going down is significantly higher than compared to the case where we didn't have the volt-var function enabled. And why this is happening? This is happening because all the customers now start to absorb reactive power before actually curtailing generation. And the absorption of reactive power helps the voltage levels to reduce even further before we actually go to the worst case scenario where it is 1.1 per unit of voltage, which is the limit, and then the volt-var starts to kick in and then curtailing generation. And you can even notice that before the volt-var is actually triggering curtailment, you can see the effect even here on the shoulders of the voltage rise, where essentially, because we are absorbing reactive power much earlier in lower voltage levels, we can see that the shoulders, the magnitude of voltage is reducing also compared to the case where we didn't have the volt-var. So essentially, this shows the benefit of having the volt-var activated as well as with the volt-var. So the volt-var tries to reduce as much as possible the voltages without affecting the customers, essentially meaning that we are not curtailing generation, and therefore it's reducing the voltage significantly before we actually go into curtailment. Now, if we talk about the utilization of the assets, we have a very different scenario here. And here, what we can actually see is that instead of actually having the utilization level being contained, let's say in very low levels, as it was shown in the previous case, we see an increment of the utilization level. And even at the very high penetration levels, at the 100% penetration, we might see some risks of assets being overloaded. And this is because on top of having, now that we have the absorption reactive power that is helping to reduce the voltage, the volt-watt function is not triggered because it's seeing lower voltage, and therefore customers are allowed to generate even more generation. And therefore, the combination of active generation in the network, which increases the current flow, with combination of the absorption of reactive power that is also increasing the current flow, it creates a combined effect where we can see the utilization level of the assets increasing. And in this particular case, we're seeing that we might, in some times, seeing assets being overloaded. However, in this particular case, for the high voltage lines and conductors, we didn't see any problem in terms of congestion of these assets. And just to compare again with the previous case, where we didn't have the volt var function enabled, this is what is happening. We are seeing that without the volt var, because we're curtailing significant generation, we can significantly reduce the utilization level of the assets. However, on the other side, if we enable the volt var, it allows us to reduce the voltage significantly. However, it also increases the utilization level of the assets. And as a matter of fact, although we didn't have any issues on the high voltage side, these particular settings and this particular case that we're investigating, it showed us that actually some of the transformers will actually face congestion, thermal congestion through the penetration levels that they are coming in the years. And this is, again, as I explained previously, because we are increasing the amount of current that is flowing to the network due to the absorption reactive power and also the generation. And compared to the previous case, we can see significantly the difference here, where essentially only one transformer was overloaded in the previous case, where in this case, we can start seeing a couple of those transformers being overloaded. Now, in terms of the effect on the customers, again, this slide here shows the active PV, active power generation of each individual customer. And if you remember from the previous slides, this particular slide here, it shows that we are able, with this adoption of settings and functions, we are able to reduce that impact to the customers. So essentially, we are having significantly less curtailment because we are helping to reduce the voltage with the absorption of reactive power, and therefore the volt var is not triggering curtailment that dramatically. So comparing with the previous case, you can see the 100% scenario where every customer is having PV systems. We can have actually PV systems that they are curtailed even down to up to 80% of their installed capacity, where in this particular case, we don't see that, that same behavior. So clearly, by adopting this functionality and settings, it can help us reduce the number of non-compliant customers in terms of voltage issues, and also increase the value to the customer because we are not curtailing that much of generation. Now we have seen the trend and the behavior for this in terms of active PV generation. Let's see what it means to the absorption of reactive power. Here we have also the figure where it shows the reactive power absorption for each individual customer with PV system. And clearly you can see that during the generation hours, those PV systems are absorbing reactive power in order to help with the reduction of voltage problems. Now, let's move into the seasonal analysis just to see a bit more of the numbers, what this means to the network and the customers. And in this particular figure, this slide here, we have on the top left, we have the number of non-compliant customers, the customers that are actually facing voltages above the voltage limits. And what you can see is that we can now see customers being affected from a very tiny number of customers throughout the year affected through voltage issues, and then that number increases to the penetration levels, where we can see up to around 30% of customers being affected in terms of voltage. Now, in terms of the utilization level of the assets, the only assets that are actually facing issues is the transformers, where as we said previously, because of the absorption reactive power that is increasing the current flowing to the network, we are exacerbating the utilization of these assets. And in particular, in this particular case, we have transformers being the bottleneck in terms of technical issues for thermal congestion. High voltage conductors and low voltage conductors were not an issue in this particular case, but the trend is obvious, where essentially the utilization level increases through the penetration levels. Now, the most important thing in this particular slide here is the effect on the customers, and how we can actually quantify this is through the curtailment levels that customers are facing using these particular settings and functions. Now, if we take the total curtailment, the percentage of total curtailment throughout the year, what you can see here, we have a minimal curtailment, which means that we are able to reduce the number of non-compliant customers in terms of voltages without really impacting significantly the customers. We are talking here about around 2% of total curtailment throughout the whole year, which means that it's a significant added value to the customers. And you can even see that for individual customers, the percentage of total curtailment is significantly low, because the median of these customers is always of curtailment, percentage of curtailment throughout the year and different seasons is close to 1 or 2% throughout the whole year. And we have only a few outliers that they had to curtail up to 30% of generation. However, in total, the whole system was facing curtailment around 2%. And given this small value of curtailment, these customers that actually were curtailed higher with higher amounts of higher levels compared to others, they could be compensated, let's say, from DNSPs, given the significant benefits that is provided using these control schemes. Now let's try to see the comparison between the case where we didn't have the VolVar function, enabled. And now this is the slide which essentially shows the same results, but without having the VolVar enabled. Clearly, you can see the number of non-compliant customers dramatically increasing through the penetration level. So here we are talking about the worst case scenario, about 90% of these customers facing technical issues, as compared to the previous case where we showed that adopting the new settings with both VolVar and VolVat enabled, it can decrease that number of non-compliant customers down to 30% in the worst case scenario. And now talking about the utilization of the assets, given that we are curtailing significant generation, none of this is facing any technical issues, except those high penetration levels where some of these transformers will be overloaded. Now, in terms of the curtailment, which is the effect on the customers, we can clearly see here this effect that is impacting significantly the customers, because on the total system curtailment, we are talking about around 18, close to 20% of total energy curtailed, just to have this solution that essentially it doesn't provide significant benefits to the number of non-compliant customers. So we clearly see that benefit that is coming once we have these new settings and the functions enabled altogether. Now let's try to see them side by side, just to really see the clear benefit here. And we have here on the left-hand side, we have the results with the VolVat function only enabled. And on the right-hand side, we have the VolVat with the VolVar enabled. And you can clearly see the benefit that comes through this enabling these functions, where you can see the number of non-compliant customers significantly being reduced. However, as we said previously, the utilization level of the assets increases slightly. And if we talk about the amount of energy that had to be curtailed, in this particular case, the results and the benefits are obvious, where we can see that in the case where we only have the VolVat, we have dramatic increment in terms of curtailment levels, where in the case with the VolVat and VolVar enabled, we have minimized the effect on the customers. We have minimized the amount of curtailment that needs to happen to the customers. So this clearly shows an added value to customers, providing as well benefits to the network. Now that we have showed the benefits that all these new functionalities of VolVar and VolVar have play into these studies, we're going to step into the effects of and benefits of adjusting the offload tab changes. And just to be clear on this, this is an added solution on top of the new Victorian settings of VolVAR and VolVAR. So we're considering that the new settings that are defined in Victoria through different DNSPs, that they require VolVAR and VolVAR to be enabled with specific settings. On top of that, we are implementing the adjustment of offload tab changes to see what this means in terms of the effects and benefits. Of course, here we have again the key findings that I'm going to try to highlight before we actually go into the results, so we will be able to understand better and focus better on those things that really make a difference. So with this application of solution, we have additional benefits to both networks and customers, and we are able, throughout the whole analysis that we have done, through all the networks that we have, to shift the hosting capacity to at least 40%. And also, this allows us to reduce as well the annual curtailment to 1% only. And of course, given that this solution does not tackle any thermal issues, it doesn't provide any solution in terms of mitigating acid congestion. So let's jump into the results and see the single day analysis. We'll have exactly the same scenario as we showed with the previous cases as well. So what you can see here is that from 20% penetration that we showed previously that we're able to achieve adopting only the VolVAR and VolVAT functionalities, we are now, with adjusting the offload tab change, we can now shift the penetration from 20% to 60% for this particular network. And what you can see is that even further penetrations, we can see that the number of profiles that are actually violating the limits is significantly lower. And if you compare with the previous case where we didn't have the solution, where we felt here no solution is only having the VolVAR and VolVAT enabled without any offload tab changes being adjusted, this is what is showing here. We can clearly see the reduction in voltage that we can successfully achieve by leveraging the offload tab changes. And this allows us to have more and more PV systems in the network without having violation of voltage issues. Now, this is a clear benefit in terms of voltage. Now, jumping into the utilization level of the assets, we didn't see significant benefit because, of course, this was not the purpose of the solution. It was not tackling the acid congestion of the acid congestion technical issues. And also have seen slightly higher utilization level, given that you are reducing the voltage and therefore slightly the current flow increases. Therefore, we can see that the utilization level of the assets compared to the case without any solution is almost the same. Now, going to the benefits to the customers, this slide shows that we can increase that benefit that we have shown that we can have with the adoption of the VolVAR and VolVAR settings alone. Adopting the offload tab changes, it can further increase that benefit to customers, where essentially we can see that up to 60% penetration of PV systems, none of the customers had to curtail generation. And this is, of course, because with the offload tab changes, we're able to reduce the voltage level, and the magnitude was significantly lower than it was before. The VolVAT functionality was seeing lower voltage levels and therefore was not triggered. Therefore, this solution allows to bring additional benefits to the customers, and not only also to the network, because we are significantly reducing the number of voltage issues. And again, just to compare with the previous case without any solution, this is the case where on the worst case scenario, we can see significant curtailment to a large number of these customers with PV systems, where in the case where we adopt offload tab changes, the effect is reduced significantly. Now let's see the seasonal analysis to understand the numbers there. And this slide here shows again the benefits that we have slightly introduced in the previous cases, where the number of non-compliant customers is almost solved for all penetration levels, where up to the 100% penetration, we can start seeing some of these customers being affected. And you might ask the question where we showed previously, where by 80% penetration, we're already seeing some of the customers being affected with voltage problems. These results that were showing previously with the single case analysis was the worst case scenario. That it doesn't mean that we might see it in practice. And given that the seasonal analysis that we have here, with that analysis, is using actual real information of demand and generation, it gives you a more realistic information of what this might mean to the customers and the network as well. Of course, the utilization level of the assets, it doesn't improve. It's still the same as it was before. But the main benefit here is the amount of curtailment that it was required by the customer, that it was minimized down to just 1%. You could actually, if you zoom in into these figures here, where we see the total curtailment of the system, you can zoom in and you can actually see that almost 1%, essentially 0.8% of curtailment. If you zoom in, you will be able to see it, but given the figure here is not visible to really see in this particular slide. However, it is obvious to see here that the number of customers that they actually require to curtail generation, those outliers that they were going up to 30%, now is also reduced significantly. So we are definitely showing that here there's a huge significant benefit if we tap into the offload tab changes for a solution in terms of this hosting capacity. Now, moving on, we're gonna jump into the effects and the benefits of adopting network implementation. And before we jump into the technical results, first we're gonna try to highlight the key findings, which essentially in this analysis we have seen just benefits for the networks only, and those are focusing on asset congestion. And we haven't seen significant benefit in terms of voltage reduction. This might be due to the fact of our simulation analysis and how we model our low voltage networks, which might be considered robust in a sense of impedance levels that they have in the different conductors. And this solution provides significant benefit to congestion of the assets, because we are reducing all the congestion, we're eliminating all the congestions. And however, this might be considered, this action of augmentation might consider time consuming or costly. However, every solution comes with a trade-off. So let's go into the single day analysis. We have exactly, again, the same scenario here, the same simulations. And clearly, as I mentioned previously, there's not an obvious benefit in terms of voltage issues. As well, as I mentioned previously, this might be because of our particular simulation, so it might be a caveat here. However, the reduction of voltage was not that significant to really visualize and benefit here. So compared with the previous case, it's almost the same scenario, almost the same impact. You can see a slight reduction of those, but this is not that significant. Now, the huge benefit here is when we actually focus on the utilization of the assets, where in this particular case, if you remember with the previous analysis, we had a significant amount of transformers being overloaded, and now these ones are never being utilized higher than their rating, because you have replaced them to higher capacity transformers. And in terms of the customers' impacts and effects, we are almost seeing the same effect as it was with the business as usual. And business as usual, again, refers to the case where we only have the volt-VAR and volt-VAD enabled. And just to compare again, this is the same results as it was with the previous case. Now, the seasonal analysis, just to give some numbers. In terms of the number of non-compliant customers, we still have the same performance with the previous cases. However, you can really see the clear benefit in terms of the customers that they are, in terms of the transformers that they are not overloaded anymore, because we have replaced those that they were affected. In terms of the total curtailment, we still have the same performance as with the business as usual. So we are not impacting further the customers, neither we're providing more benefits to them. However, we're able to solve the thermal issues that in the previous cases we will not be able to solve, because we're tackling only voltage issues. Now, just to understand what level of augmentation required for this analysis, for the high voltage conductors, you only had to replace up to 700 meters of conductors to the worst case scenario, up to 100% of PV systems. And in terms of the transformers, through the penetration levels, we had to replace around 2 transformers up to the point where on the worst case scenario where we're seeing more and more transformers being overloaded, we had to replace 12 of these transformers. Now, having finished all this technical stuff, I will jump into the conclusions just to summarize again what we have seen through this analysis, and then I will focus on the next steps of this project. So on the conclusions, what we have seen is that the new Victorian PV inverter settings can provide significant benefits to both customers and networks. And we have seen that we can achieve at least 20% of PV hosting capacity just with these settings alone. And this is done with a minimal curtailment, which means that customers are not affected significantly. So we keep the value of customers when they actually buy their PV systems and they want to generate as much as possible. And with these solutions, which are referring to the new Victorian PV inverter settings, we can clearly reduce the voltage issues without impacting significantly those customers. Even further than 20% penetration, these settings allow us to reduce the magnitude of the voltage problem. The voltage level is reduced significantly, and also the number of customers that are actually facing these technical issues is significantly lower than the previous cases. Now, the only, let's say, caveat in this particular case is that with this solution, with the VoltVar enabled, we are absorbing reactive power significantly, and this might increase the current flow into our networks, and therefore might exacerbate the the utilization or level of the assets, which might risk some congestions in high penetration levels. Now, tapping into all load tap changes and offload tap changes, it allows us to increase the benefits to the networks and the customers as well, and this translate to at least 40% of PV hosting capacity at the least case scenario, which means that we have 20% more of customers being able to install that PV technology. And we are also further reducing the curtailment that was required to manage the voltage issues. And this accounts to just 1% throughout the whole year. Beyond that 40%, again, the voltages are kept to low voltage levels, and also the number of non-compliant customers is reduced significantly. Given that we are reducing the offload tap changes to a lower level, and that is not automatically changed until some engineers go and change it, this means that we might in the future face under voltage issues. So given that in the future new technologies are coming in, that they are impacting the voltage level to a lower level, such as future loads, electric vehicles, or new houses, this might be a caveat as well in this solution. However, this allows us to understand the level of effects and benefits using these particular solutions. Now, in terms of augmentation, in this particular case, we have seen benefits only for the networks, and those are focusing on asset congestion, given that we are directly replacing those assets that are overloaded with higher rating assets, and we have seen minor benefits in terms of voltage levels. However, this might be considered time-consuming approach or costly, but as every solution that we have shown previously, everything comes with a trade-off, and in these particular cases, we can consider that it might be a combination of augmentation and offload tap changes might potentially help us to shift the hosting capacity beyond 40%. Now, in terms of the next steps, we still have to work on 3 more tasks, which is task 4, 5, and 6. Task 4 is the current task that we're currently working on, which is focusing on adopting non-traditional solutions. And what do we mean by non-traditional solutions? Are solutions that they focus on new technologies, such as replacing offload tap changes with on-load tap changes in low voltage substations, utilizing a new emerging technology, such as the residential battery storage systems to manage the exports of the household and therefore the voltage levels and the congestion of the assets. And task 5, what it's actually going to focus on is to try to understand the cost of implementing any of these solutions that we have shown and try to compare with the different methodologies and solutions that we have shown in the previous tasks. Task 6 will try to sum up everything and provide recommendations for the DNSPs. so they can be more prepared and also take more informed decisions when they are considering such solutions to increase their hosting capacity of their networks. In terms of the technical reports, everything is available online through ResearchGate and also through the project website, either through ARENA website or the University of Melbourne website. You can click on these links and you will be able to access the detailed reports where they provide all the information that is required for this particular task that we have completed. So at this stage, I would like to thank everyone for joining us for this webinar. I hope you found it very fruitful and you had a very informative session here. Thank you very much. Nando, if you want to say any last words?
Sure. Thank you very much, Andreas, for the presentation. As you all can see, there's a significant amount of results and simulations. The webinar was just presenting the results for CRE21, which is an urban network. We have a very interesting set of results for the other networks, particularly the SWARE lines, those that are rural, are quite interesting to see what is actually happening to the customers, to the voltages, etc., etc. Also, again, please note that this webinar did not present what is happening when we use the on-load tab changers at the primary substations, at the zone substations, but this information is all in the corresponding reports. Well, finally, also remember, as much as it is very promising, everything that has been shown today because of the new Victorian PV inverter settings, we need to be very, very mindful that all our simulations consider that these settings were enabled from the very first installation of a house with photovoltaics. In reality, that is not going to be the case. In reality, we'll have a mix, a penetration of, I don't know, 10 or 20% already with the old settings. And the new settings will go on top of that for the new installations. That will mean that we will have really actually different values of hosting capacity and different impacts on customers. But nonetheless, that doesn't mean that we are not going to see better behavior of the network or the interaction of photovoltaics with the network because of the settings. The settings are going to bring significant benefits to both customers and networks. And hopefully these settings will be also adapted, even if similar settings in other states of Australia and perhaps around the world, because these are very good settings. Of course, we will look at other opportunities and other settings as well in the next task, which is non-traditional solutions, as Andreas mentioned, but that will be in a few months. So for now, thank you very much, and we appreciate you joining us in this webinar. Bye-bye.